Well, hey everyone, and welcome back. As I promised, this video is going to be a continuation of the last video that simply details how to draw a cross-sectional surface diagram from a topographic profile if you include these sections of strata that I've laid out here. So I tried to keep this map relatively simple because we've got even more lines going on. We've got the dashed ones representing our contour lines, and the solid ones representing the contact boundaries between our different strata here, A, B, C, D, and E. And then, of course, we've got our thick line X and Y, which is our area of interest. So right off the bat, the first thing we need to cover is the strike and dip of this surface here, because that's going to be important to us when we actually draw the strata into our surface diagram. So I'll just draw this here. This is a strike and dip symbol. The longer line represents a strike, and the short line perpendicular to it represents the direction of dip. And then generally you'll have a number written somewhere near it, such as, I don't know, 30. That'll give you the angle of dip. And if you just place this onto our profile here, then you can just use the directions to let yourself know in which direction the strike and the dip are. So I'll just put a little compass up there. North, east, south, and west, typical compass orientation. So in this example, I'm going to have all of our strata dipping in the same direction, and that's going to keep things incredibly simple for us. So you'll see what I've drawn here is just the strike and dip symbol, such that the dip goes with the line we've drawn here, and the angle of dip is 45 degrees. And that's all we really need to establish before we start here. So I'll just draw the outline of our surface diagram here. And we can start with our vertical axis. And just like last video, we're going to see which one of these is the highest. If we look at this line here, this one is at 70, and since this goes beyond 70, and this must be at some point higher than 70, so we'll have 70 be the highest marked value. Since we never have a line that goes up to 90, we don't need to mark that on it, but it's good to know that there is likely a point where it goes up, maybe up to 80, maybe somewhere between 70 and 80. And then our lowest point, if we look here, 70, 50, 30, okay, whoops, 10, and then it stays at 10 and then starts to go back up. So 10 is going to be our lowest value. We'll keep that. We won't have 10 be the bottom this time. We'll actually have the bottom be 0. And I'll just try to draw in the rest of these. Hopefully I can do this better than last time. 20, 30, 40, 50, 60. Okay, that looks pretty good. It doesn't have to be perfect. If, like I said a million times last video, if you were doing this in a real problem and actually trying to make a decent surface diagram, then you would actually want to measure things out and make your scale as exact as possible, and make the distances between them actually equal. And then I have up here our horizontal scale. 1 inch is 300 meters, so if we just measure the XY line, that is about 0 inches, about 9.5 inches. So let's see, 9 times 300, 2,007, that's 2,850, or close enough to 3,000 meters across. So we'll have that be our maximum on this edge. Once again, right there is 0, and I guess we'll go up by 500s. 500 there, 1,000 there, 1,500, 2,000, 2,500, and once again, the space between these two looks bigger than the space between those two. It doesn't have to be perfect in any way, just gets the idea across. And now we're just going to start drawing the surface as we did in the last video, just by looking at where the line meets certain contour lines. So there's about 2 inches between the start of A, the start from point X on line XY to the point where it meets the 70 contour line. So 500, that's about, just draw that up, maybe about right there. And then between the 70 and the 50, we've got about 1.5 inches, so we'll call that 450, so we'll go a bit over 1,000. That's where we reach 50. And then between the 50 and the 30, we've got just about 1 inch. So about another 300, that gets us almost up to 1,500. Put that right. More like right there. And then from 30 down to 10, that's about close enough to 2 inches, so we'll say that goes up to, it's another 600, almost to 200. At the point it reaches the 10 mark. And then between the 10 and the next 10, that is about 1 inch. So we'll go up another 300 to about right there. And then the final piece of it is about 1.5 inches. So that'll bring us another 450, so we'll be about right here. And we'll be somewhere between 20 and 30. Yeah, somewhere in there. Looks like we almost get up to the 30 contour line, so we'll be closer to the 30. And now we just draw in our little line. We'll just say we start somewhere up here above 70, but not to 90. Just draw our line down, connect the dots. And of course, if you wanted to, you don't have to make this look so connected. You could just draw line, 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 you know, in that fashion. So this is the end of our profile for now, which makes sense too, because the actual line was 9.5 inches, so it was more like 2,850 meters as opposed to the full 3,000. So it looks like our scaling actually turned out pretty well this time. But now we actually have to draw in the strata. And the first thing we have to do is just look at, well, at point X we're still in strata A. And it takes about 1.5 inches or 450 meters before we reach strata B, or the boundary between them. So we're just going to go up here and draw our first line, maybe right there, slightly before 500, and we'll label this area in here A. Right now we're just drawing what we see at the surface. That's how much of A we see, and then B is clearly bigger. So that's about 3 inches. That's, let's see, another 900 meters, so we're going to be somewhere in here about. So between these two is B at the surface, and then between these 2 points to make C, that's about 3 inches again, so we'll go up another 500 or so, excuse me, 900, bring us maybe around right there. And then all the rest we know we're just in D. And now we know that the dip is 45 degrees, so we can actually draw what these look like below the surface, because you'll recall that the dip is the angle that the strata makes with the surface. So if we know that the dip is 45 degrees, well, we can say that it looks something like that. So we just kind of draw a little angle in there, and then just make a line that follows an angle parallel to that of A for B. That's not the correct point. Right here at this line, just draw that down. Once again, doesn't have to be perfect. And then draw that down for C, and since we never reached the actual boundary of D, we can't be really certain of anything below the surface. And now we can just sort of draw in our strata letters into their actual boxes, A, B, C, and D. And then you'll notice this starts to look more like an actual cross-sectional diagram where we can see dipping strata, the points at which they reach the surface. You know, you could measure thickness, vertical thickness, etc. all for this. And it would all be fine and dandy. And one of the things that may be a little bit confusing at first is, well, just looking at this map, we see that A, it doesn't appear that much smaller than B. And that's right, because that's simply at the surface and the horizontal distance that is covered at the surface. So you'll see that A, this distance actually isn't much smaller than, like, this distance. I mean, it's not, there's still a decent difference. B appears to be about twice as big as A. But it's not as huge of a difference as the area below the surface that we see of A compared to B, wherein B looks maybe 10 times as large as A. And that's just because the topographic profile only gives what is seen at the surface. So using this can give you a much more holistic picture of, okay, A covers maybe close to half as much horizontal distance as B, but since B has this huge vertical distance here, and since they're both dipping at the same angle, we're going to see a much larger chunk of B than A in this selected area. And then the same goes for C. C appears to be just as large as B. In fact, I think they both measure to be about 3 inches on the surface. But since B has so much vertical height here, we're going to see a lot more of it on this map. Obviously, all of them extend down further below this, but, you know. And that's basically all there is to this. Oh, I will mention, though, that if all of your strata were not dipping evenly, you would need more information to be given, and you would most likely have to look at other cross-sections of the strata in order to determine, okay, which one was deposited first. So maybe you would have to date them or something. Because think about it, if, for example, C were at a lower angle than B, and it were going kind of like this, then, well, they both cut off from the same place. You know, the boundaries are at the same spot, but in this case we would have C cutting over B, and we would see less of B and more of C, where in this case, the case that I provided you with, we would see more of B than we would C. So it does become, you would need to know which one was deposited first in order to say, okay, which one would be cutting over the other one. Or you would need to be given, okay, B extends to this depth at this point. So if, like, at this point we say that B only extends to, I don't know, maybe that's about 15 meters above sea level, as opposed to much farther down as it would be in the original example, you know, we can say, okay, C must be cutting over B rather than the other way around. But for the sake of this simple example, I just used uniform dip. And you'll see many instances like this. The world isn't always complex as it can be. So, you know, you'll see things like just nice multiple strata that have all been folded together so they all have a nice uniform dip. But I'm just rambling at this point. Hopefully you guys enjoyed. Hopefully it was informative. Otherwise, good review. And I'll see you all in the next video.